Hello world, Liu here, and today let's talk about a simple algorithm you absolutely must know for coding interviews, which is graph search. So here, graph search includes both breadth-first search and depth-first search. I'll first show you how this works on pen and paper, and afterwards, I'll translate these diagrams into Python code. If you're new here, I'm a software engineer from Singapore, and I create content that aims to bring your Python skills to the next level. Now, back to the video. So first, let us understand what a graph is. So back in school, we probably learned that a graph is something like this. So this is the y-axis and this is the x-axis, and then you have this quadratic curve or something like that. So in programming, a graph does not refer to this graph. Instead, in programming, a graph is a data structure that contains nodes and edges. So let me give you a simple example. So let's say A, B, C, D. So I'm going to draw circles here. And I'm going to draw lines between these circles. So here, these circles are nodes, while these lines, they are edges. So sometimes we call nodes vertices, and you can call them either. Also, there are different types of graphs. There's going to be weighted versus unweighted graphs. So here, let's say I have A, B, C, D, and let's say I have this versus A, B, C, D. So next, I'm going to add a bunch of numbers here. So let's say 2, 3, 1, 4, 1. So here, this is an unweighted graph, while this is a weighted graph. So here, unweighted just means that all of the edges have the same value. However, in weighted graphs, this has more weight than this. Next, let's also talk about directed versus undirected graphs. So let's say I have A, B, C, and D, and let's say I have this. So here, this is an undirected graph, which means that A can go to B and B can go to A. However, next I'm going to draw a directed graph. So I'm going to use arrows. So A points to B, B points to C, C points to D, D points to B, and D also points to C. So here what's happening is that A can go to B, but B cannot go back to A. B can go to C, but C cannot go back to B. C can go to D and D can go to C. So this is a directed graph. So today, for simplicity's sake, let's assume that our graph is unweighted and undirected. And next, I'm going to draw our main graph for today. So here we have A pointing to B, and B pointing to C, D, and E. And afterwards, we have D and C both pointing to F, and we have G on the side, pointing to H, and then I, and then back to G again. So this is our graph. So here, a node represents a person. So A is a person, B is a person, C is a person, G is a person, H is a person, and so on. And next, an age just means that these two people recently met. So what's happening here is that A has a virus, and anyone who he meets is at risk, which means B is at risk. Also, anyone who meets anyone who is at risk is also at risk, which means that C, D, and E are also at risk, and F is at risk. However, G, H, and I in the other network are completely safe. So here we can actually solve this using graph search. So the very first thing about graph search is that we need to have a queue that contains our first node. So this is our queue, and this is going to be A. So here what happens is that our queue will be first in and first out. That means if we put A in first, A will come out first. And next, we are going to remove A from the queue. So A comes out, and we search its neighbors. So over here, A only has one neighbor. So neighbors are B. And since we haven't searched this B neighbor, we add B back into the queue. So B comes here, and this is the first iteration. So next, let's go on to the second iteration. So we take B out of the queue, and we search B's neighbors, which happen to be C, D, and E. So here, B's neighbors are C, D, and E. So next, we add C, D, and E back into the queue. So here, notice that A is also B's neighbor. However, we do not add A because we have already seen A. And next, we search C. And next, for C's neighbors, we are going to get B and F. However, we do not add B back into the queue because B has already been searched over here. which means we only add F back into the queue. And next we search D, and we are going to get B and F also. However, we do not search B because we have already searched it. So F gets added back into the queue also. And next we search E. So E's neighbors are going to be B only. And similarly, we do not search B. And next we search F, and we get C and D, which we both do not add back into the queue. So here, notice that we search A, B, C, D, E, F. And we have searched all the nodes in this network without searching this other network over here. And from here, we can establish that G, H, and I are actually safe. So next, let's actually translate this into code. So first things first, we have to translate our graph into a data structure. And to keep things simple, let's use a dictionary. So I'm going to call it G for graph is equals to a giant dictionary. So A will point to B. And next, B will point to A, C, D, and E. Next, C will point to B and F. And D will also point to B and F. E will just point back to B. And F will point to C and D. Next, G will point to H and I. H will point to G and I. And I will point to G and H. So here, this is a representation of our graph. And next, let's actually do our graph search. So I'm going to define GS, which stands for graph search. And here we are going to have starting point. So first things first, we start with a queue containing our start character. And also, since we have to keep track of what we have already seen, let's use a set to do this. So seen is equals to set. So as long as there is something in the queue, this signifies that there is still something to search, which means that we use a while loop here, and while length of queue is more than 0. So here this while loop will run forever and ever until queue runs out of stuff. So here, let's call it current is equals to queue dot pop 0. So what's happening here is that we remove the first thing in the queue and we set it to current. And next, if current in scene, we continue. Else, we add current to scene. So scene.add current. And afterwards, we need to search its neighbors and put those that we can back into the queue. So neighbors is equals to G, which is the graph, current. So here, I'm going to print neighbors, and I'm going to break just to show you. So here, GS, and I start with A. And if I run this, I'm going to get B. Here we only get B because B is A's only neighbor. So next, for neighbor in neighbors, so if n not in scene, we add the neighbor back into the queue. So queue dot append, because it's a list, n. So here let's run one iteration and let's see what happens. So here let's print queue, and if we run this, we should get B. So right now our queue only contains B. So next, let's remove all of this and let's print scene at the end. So if I run this, I'm gonna get A, B, C, D, E, F. So here I'm using a set, so the order is a bit jumbled. So let's actually inspect this step by step. So I'm gonna have an input, and here I'm going to print queue. So here before pop and after pop, and here I'm going to print scene, and afterwards I'm going to print after adding neighbors, and I'm going to print queue again. So let's run this bit by bit. Next, let's also create an iteration is equals to 1. So here I'm going to print iteration, and at the end, iteration plus equals to 1. So here let's add iteration, and before this, let's add a bunch of equal signs. So let's run this. So here we have iteration 1. So here before pop, our queue is going to have A, and after the pop, our queue is going to have nothing. Scene is going to have A only, And after adding our neighbors, our Q is going to be B. So let's move on to the next iteration. So iteration 2, before we pop, we have B, and after we pop, we have nothing. So at this point, scene has A and B. And after adding B's neighbors, C, D, and E, our Q will contain C, D, and E. Next, iteration 3. So here, before pop, we have C, D, and E, and after pop, we only have D and E. So after adding C to scene, we have A, B, and C. And after adding neighbors, we got D, E, and F. So this goes on to iteration 4, we have D, E, and F, and we remove D from the Q. And after the pop, we are left with E and F. And after adding neighbors, we will have E, F, and F. So let's do this. So F, 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 and here we have our final iteration. So here, our scene contains A, B, C, D, E, and F. So notice that G, H, and I are untouched because they are in a separate network. So next, I'm going to remove all of this other code. So let's do this, and let's shorten this into one line. Let's shorten this into one line. So let's remove this. So let's remove this, and let's remove this too. So here we return scene. So if we run this once again, we are going to get A, B, C, D, E, F. However, if our starting point is a G instead, we will get G, H, and I. So this is for the other network. Similarly, if we start at, let's say, E, we should get A, B, C, D, E, F too. If we start at F, we should also get A, B, C, D, E, F. And next, you might have heard of these two terms floating around, breadth first search and depth first search. So here, what we are doing in this code is actually breadth first search. And it's breadth first search because we use a queue. So here, if we want to replace this with a depth first search, we use a stack instead. So here, instead of popping 0, we pop the last thing in the stack. So if you run this, we'll still get the same thing, but the order at which we search the nodes are different. So here, let me visually explain the difference between breadth first search and depth first search. So here, let's say I have a bunch of people. So A, B, C, D, and I have E, I have F, I have G, I have H, J, K, let's say I, L, M, N, and O. So I realize my alphabets are screwed up already, and so on. So here, let's say we start from A, and let's say we do breadth first search first. So what's happening is we search the nearest neighbors first. So A first, B, then C, then D, and then E, F, G, H, J, K, E, F, G, H, J, K, and then these neighbors and whatever neighbors we have over here. However, in depth first search, we'll first search A, and afterwards we'll search B, and we'll go downwards first. So B, E, I, and so on, and until there's nothing left, then we'll search F and L and so on, and after there's nothing left to search, then we'll search C, G, M, and so on, and then H, N, D, J, O, and then K, and whatever is here. So here, just by changing our queue to a stack, we can convert a breadth first search to a depth first search. So once again, thanks for watching, and hopefully this was clear and easy to understand. See you in the next one.